Welcome everyone to this live stream, to an amazing FPGA and RISC-V update. You probably have seen in previous live streams here this amazing icebreaker FPGA board. We unboxed it, we did the first enablement, we packaged all the open source bits and pieces of Clifford Wolf and all the other contributors there of Yosys, FPGA, Synthesis, Place and Root, and all those tools there. Quite an enormous live stream. And maybe you either want RISC-V or play with FPGAs, learn and tinker and invent, or you're just super tired of Intel CPU bugs because they can't even get caches and jump instructions right anymore, and you finally want to do better, then this live stream is for you. So we take here for this huge shout out to Estin here for sending this amazing getting started, affordable small entry-level FPGA board here over for just something like $69 or so if you want to play along at home. Although he sent it for free because he's amazing. So we take this. Previously we have just taken a look, so I will try to keep this live stream relatively short. So if you want to see all the details, unboxing this, and getting this first open source toolchain stuff installed and working than previous live streams, maybe 3 or 4 of those. So I finally found the time, because ideally one of those toy projects would be to do your own CPU, and for this of course we turn to RISC-V. I made already a previous live stream. Let me just check how we are online in case we are mostly live stream. Welcome everyone, Christian. So RISC-V, I made a previous live stream also, not only about RISC-V, but also about the instruction set architecture and how this compares to MIPS and SPARC and x86. If you are into that previous live stream, also open source. So what has all of this in common? Everything of this is nowadays open source, which certainly is totally amazing, especially if you have Intel CPUs with so many bugs nowadays and you finally will want an open source CPU. And yeah, RISC-V, I went over this pretty nicely sorted instruction set architecture. And of course we are not doing this here overnight out of thin air. We are standing on the shoulders of giants here, of not only doing all the reverse engineering for the FPGA bit stream, because until recently only vendor, binary only, proprietary, not amazingly working toolchain. So nowadays Yosys and also Clifford Wolf of not only Rock Linux but also Yosys open source FPGA synthesis fame. They are so amazing. He has done even not only all the infrastructure toolchain like the GCC of open source synthesis, but also implemented here a Pico RV32 Pico RISC-V, a size optimized RISC-V, because this is an entry level, well at least I call it, correct me if I'm wrong, entry-level FPGA with only 5,200 something, which we could fact check here, 5,200 something, 5,280 logic cells for lot carry FF. And so with only this, it is already amazing that we can get a whole processor on that. And I finally tested this, so I've not done anything except compiling all this information and testing it for you, and we will also expand on this. So how does it work? If you have something like this, either the icebreaker or a similar vendor FPGA development board like this, then you can just git clone here, GitHub, Clifford Wolf, Pico RV32, actually Pico, well, this repository, this Git repository, and then Pico RV32 SOC. Wait a second here. So what this is doing is on top of the CPU core. So Pico RV32 is just the CPU core. If you want to use it on real hardware, you need a little bit of surrounding, like a memory controller, maybe some flash serial interface, and that is what this Pico SOC is doing. Pico system on chip, what you usually buy there from some companies like Broadcom, Samsung, Imagination Tech, all the other SOCs. But we want to do this ourselves. And so not only has he done this amazing tiny and small Pico RV32 core for us and you to use, but also the surrounding stuff, including test firmware. So you just git clone this here, as you see here in, let me just double check, could also position this slightly more perfect, because certainly we are perfectionists. And so you get some hardware like this, install all the open source stuff, previous live stream, for example, even in our unsuccessful Woman distribution, everything nicely packaged and working. And then you, for example, enter here in Pico SOC and make some targets. So there are a couple of targets for different boards, and we make here this icebreaker IceB proc. This target directly flashes it to this board, and for this we plug it in also here to our USB port, and then run this here, Pico. So when you run this the first time and it's creating synthesizing all the FPGA design, this actually takes, maybe this is an aging Core i7, so on the AMD Ryzen this might take a minute or two. On this aging Core i7 it might take 10 minutes. But if you run significantly larger FPGA designs, it's synthesizing certainly 30 minutes or a couple of hours. And as you see on this screen, this was only I could actually theoretically make clean and show you the synthesizing, but anyway, it's just some log output, so that is not the most interesting. When we take a look now, we have here this blinking board. You have seen on the previous videos, which probably we could also theoretically focus slightly more maybe on our amazing open source desktop setup there. So what you see now, so this is now flashed and working, and as you see from the output here, which let me check, which I still need to sort, it's better sort here my camera views another day. Of course we have a knot in the USB cable, best preparation here only on this channel. And this you need for you to play along at home. One mistake while I was searching a couple of extra minutes was that the proc icebreaker, and then here's this 1 Mbit additional quad channel double data rate or something, 1 megabit or so additional EEPROM for the firmware. So that is an additional flash there, as you see. So that is what is missing, but this is to read the freaking manual and make files. So this is a FPGA bit stream, what we have synthesized here. We can also take a look how this looks in a second. And then the firmware, actual C firmware that we can now program ourselves with games and stuff. And I will tell you in a moment also what are my next plans and steps in weekend fun and night and weekend fun here. If we want to see now something, so of course right now it's only blinking what have we achieved, which also we could probably focus a little bit better. So what have we achieved over the other examples? The other examples of course were outputting also blinking lights. Hello, I have USB cable here. So we have what we have achieved previously, our lights were already blinking, and now, because previously this was programmed with logic elements of the other getting started examples, and now we are blinking this from a C program. And we can also, we now have, like right now, we have already fully running a RISC-V. So this is also, fun fact, this is the first RISC-V silicon, which actually don't even, where's my other camera? Hey, there's the camera. So this is my first RISC-V silicon that I actually have, not any other RISC-V silicon in here, but probably sometime soon. Anyway, is this even fully focused? Maybe not. And we can connect. So we have in running make here, we have synthesized the FPGA design. We have cross-compiled the firmware with actually also fully open source here, not only GCC, but actually compiled with T2. So I have actually patched the makefile here a little bit. The original makefile was running RISC v32 unknown elf GCC. I didn't have this. Certainly I could have downloaded their pre-compiled something there from RISC-V something org, but we are fully open source here. So I used our T2 here in user source T2 configured actually is a 64-bit RISC target, and added this to the path, and here with T2 user source T2 build. So this is freshly cross-compiled just yesterday, and here cross CC of, actually I'm not seeing this because you get the idea. And for this I patched the makefile slightly. If you want to play along at home, I will also send this actually to Clifford in an hour or two. So I changed this here, patched this from RISC-V 32 unknown F GCC to RISC-V 64 to a variable. I will send this to Clifford in a moment. And original the C flags here were march RV32 IMC, and this doesn't compile with our 64-bit defaulting GCC. So I additionally patch this here to C flags. In any case, it's certainly nicer to have variables in the makefile. So there you see, if even you can usually make stuff working, and also for you to tinker and think and stuff. The reason I've done this is because the last time I checked, the 32-bit target was not upstream in GCC. Maybe nowadays, that was 6 months ago, so maybe the last 6 months it looks like maybe the RV32-bit target is now upstream in GCC, but I did not want to spend my time of hours fiddling around and integrating this in T2 and testing this. I knew this 64-bit target works in T2, so that also works for you, just like with a AMD 64 or PowerPC Spark MIP64. You usually can in GCC say -M ABI or Arch and select a 32-bit target. And I'm actually surprised this worked. I was not expecting this so much too. Where is all the time going? Yeah, 1 hour there, 1 hour there, unpacking, testing and stuff. We can also, because we have a full RISC-V target running, RISC-V CPU, this firmware is actually C-compiled firmware to assembly and machine code. The previous examples of this here had these LEDs blinking statically or HDMI output as per the clock frequency and divider, like dividing by 32,000 something, and just having blinking these LEDs there on a static pattern. But now we have a CPU core, and we can actually connect here. Let me just check which other of this many, maybe this scene. So screen dev TTY USB, this is here the USB cable with FTDI USB chip here. So screen on the virtual USB device, serial with a very high baud rate, and press enter to continue. So Pico SOC, we now have, as you see, firmware running on there, total memory 128 kbit. That is actually the whole amount of memory that this FPGA board has. And we can now, this is example firmware. Of course, we could now compile a game, write a game, which actually, don't forget to share, like, and subscribe to do this next. Run some simplistic benchmark. And the difference, of course, there you see the difference between hardware of fixed function hardware and a flexible programmable CPU core. And what I want to do next, of course, here are other stuff like memtest. Here running memtest passed. Echo UART here, so this is a test. So what this is doing is receiving stuff on the UART and sending it back. Exit with exclamation mark. This is only my first test of validating that the toolchain actually worked. You see so many variables, uses, the synthesis, and getting into this FPGA programming and actually testing that all the bits and pieces, including a RISC-V compiler here. Yeah, this is also running all configurations, probably this one here. So that is testing here dual quad port, quad DDR configurations, and some benchmark. Here was this 9. Oops. 9 is, yeah, cycles instructions. So we are running, I think it runs like nearly 1 second. I'm not sure. I've not yet read the whole source code for that. But we are running here some, this is in hex, and instructions. So that is, of course, when we calculate this from hex, so this is right now hex. So this is some 2 maybe 2 megahertz, not sure. It looks like 2.2 megahertz, maybe, at least on the instructions. So this is 2 million, not instruction cycles. So this is most likely running at 2.2 megahertz right now, I guess. And this, because this is a very small implementation and requires quite some cycles for each instruction, this is not resulting in 2 million instructions. So this are right now maybe 253,000 instructions per second, because this is not a performance but size optimized Pico RISC-V core. I can show you some details here how the source code looks. Welcome everyone. Someone wants open source drivers, RedV Mesa driver. I'm still beginner, C++. Maybe we do this questions in the end. My poor FX would probably take nosedive and crash and flames time too. Actually, the FX is not too bad. This is a Core i7 Mac Mini, my recurring joke here. This is just our test workstation here, which I'm still using. So probably your FX, AMD FX is maybe even faster than this Core i7 part here in this 6 or so year old Mac Mini. You see even a bloody Mac Mini can do this. Study to be able to do this specifically. I answer these questions in the end to keep this stream more streamlined. Let's see, quit or disconnect. When we probably have a log here. Let's see if this log is. So what are my next? Yeah, this looks like the log from the synthesis. Is here the total time? Maybe not. So one thing, my next steps are what I want. So of course you can tinker also. I'm not showing this because, yeah. Of course I want to, first of all, to give you an overview how those bits and pieces work together if you want to play along at home, to inspire you to also tinker, program like questions in the audience on AMD Vulkan, Linux kernel drivers, FPGA synthesis, so many cool things you can do nowadays on desktop Linux in 2019. And also how this looks. So Icebreaker V here is this Verilog, and this is a source code here for the Icebreaker module, defining here the outputs, LEDs, flash, and stuff like I/O, memory, modifiers like for serial. This is just to give you an overview. Of course, this is not in 15 or 20 minutes as usual. I give a summary, then we're already 20 minutes in. This is how Verilog looks. You just define here the clocks and outputs and stuff. And then, of course, this is not all. This is also here configuring the PicoSoc module. So for example, it's disabling the barrel shifter, which is a more high performance optimized shift instruction, and multiply and divide. So the core that we have synthesized is not including the multiply and divide instruction, which is optimal to keep the logic element gate count down there. And this is a Pico RISC-V configuration. And with this is already a super size down, again without multiply and divide configuration. And when we take a look here in the synthesis here running, here of course, let me a little bit on the border, synthesizing here this IS40, and this prints, as you've seen in the Hello World example, this prints how many logic elements are used. After here, the synthesis here runs quite some 10 minutes on this 18 Core i7 Mac Mini. But again, even on this old piece of hardware, you can still run it. Let's see, used. Nah, so many. It's not what I wanted. Where is logic element? When you're looking for something, yes, it prints a utilization somewhere at the end, which of course is not immediately where I would see it. Here. So total number, this probably, wait a second, number of nodes. Hello, is this, why is it not here? Am I looking in the wrong log or ABC results? So much to not running at fresh. How many other logs? But we have only this log. So what I wanted to say is that this configuration already consumes quite some thousands of logic elements, although I don't find it right now in the log. And this is already quite some. So what I actually want to do next is extend this. You have seen in the previous live stream here of this goodness. We also have our HDMI PMOD here, probably this one, I think. And so I would want to create this in a 8-bit guy kind of programmable microprocessor system also for graphic demos and maybe even games and stuff. And for this we need some more games. So I checked this yesterday. So my next thing is, right now we only have a serial terminal here. Let me see, what other scenes do we have here? Maybe this. And so right now we have only a serial output. So next I would add here this HDMI PMOD here that we plugged in already, previous video, previous live streams. And this PMOD, there are examples to output moving ball or lines. And next I would try to create a tiny GPU outputting some text mode and maybe even potentially graphic mode. So, but for this is then real programming. Right now I've only tested this examples to bring you an overview for you to play along at home and show you how this stuff works. So next would be some real programming. That means taking this HDMI module, adding this to the Verilog here, and this would look like adding here a file, like in the simplest form, just copying this HDMI output PMOD here into this Verilog example, changing the make file to also build it here along with the Pico RISC-V core. And then of course it doesn't work so easily, so this is a little bit challenging. So because we use, I think we use maybe some 3000 logic cells, which it's a pity I don't find here right now on the log. Yesterday I saw this. We could of course make clean and let this run. Do we show this? Yes, we show this. Make Iceproc. So now it's running the who will use the synthesis, and this will probably run some 10 minutes. I hope we don't get too many drop frames while we do so. And so the challenge is how many logic elements we have left, because quite some are taken by the RISC-V core, and I think the HDMI output example had some 800 logic elements used to output this moving lines and balls. And of course we can delete most of this. We delete the lines and we delete the moving ball. That frees some logic elements, certainly, but we will need much more. So the challenge is, I was thinking to, a little bit like the 8-bit guy, create here some homebrew system of running. Of course now the synthesis stuff is running, so yeah, this is this. Which, yeah, it targets here a frequency of 13 megahertz. Editing ports with timing budget for target frequency 13 megahertz. That's probably defined in the makefile maybe. And you see we have here 4000, even 4000. So we are running a little bit out of logic elements here for this project. Need to check if we can further reduce the Pico RISC-V core, but I think this should still be doable. Just that you see it's not like taking some Hello World example and you're done. Everything, this kind of stuff is really then some real design and programming to fit this all together. So next the HDMI example code, deleting the lines and moving ball stuff, and then instead adding a character generator, but this will be really tight. So I'm not sure how much graphic we can get in there in this entry-level FPGA. Maybe we need to try to trim this Pico RISC-V a little bit more down. But we have 1200 logic elements left. This also means I was thinking to have some sound output, which, yeah, maybe we are not getting much more than a PC speaker, like some pulse width modulation, like 1 or 2 tone something, if we are lucky. First we need to get some integrated video output here to this example. And with this, we also need some memory. So right now, by the way, so this is still running. Do we have 28 frames per second? Yeah. You see the synthesis is running quite some iterations to optimize the pick and place layout here of interconnects of all the huge tree structure that is this connections of wires between the logic elements. So that's what is going on right now there. So we have 5000 logic cells, 120 k-bit dual port block RAM, and so and 1 mbit. So this 128K, so right now I think the Pico RISC-V core is using this 1 mbit as memory, as system memory, so that is fully used, and this is mbit in bits divided by 8 is 128K bytes. That is already more than a Commodore 64, for example. And I think we still have this 120 k-bit dual port block RAM. So most likely we will try to use this 120 k-bit. That of course does not leave us much room, because I think we can, because this is single port memory, my understanding is we can only access this one at a time. If this is already used by the CPU core, we cannot additionally connect the HDMI output to that, is my understanding, but correct me if I'm wrong. And so 128K bit divided by 8 is maybe 15K. So you see there is not so much left if we use this dual port block RAM as memory, which probably a lot is already used for registers, I guess, so not even all of this. But somehow we will try to create some at least character output, and maybe if we want graphics, that would be like some tiled like Game Boy or NES kind of graphic, to not have a video memory, video graphics of all the pixels, but couple of sprites that optimize the memory use, kind of like on the Game Boy or NES or something of that sort. Anyway, this is a challenge now, designing it so that we somehow get some graphic output. Character graphics should probably be doable, I hope somehow. Anyway, we need to squeeze this in, but that is upcoming for the next videos. And if you find this interesting, so you see it moved here 335 cells around, legalizing relative constraints. Here you see wire lengths, timing costs. This is what it's iteratively optimizing. Here's a FPGA layout, and it's still running, and dropping our frames a little bit. Leave me in the comments below. So certainly I'm inviting you to play along at home. This is all open source. As I said, so far we only stand here on the shoulders of those giants who created this, and certainly we are usually doing C++, assembler and stuff like that here. So FPGA, although I've done this in the past a little bit at university and stuff, but certainly not something that I'm super fluid here, but certainly super fun to play as a hobby in lunch breaks and afternoons and weekends and stuff. You certainly, if you find this interesting, you see nowadays everything open source, totally affordable to get there to play along at home. And if you have ideas and wishes what to do, you see we are a little bit constrained here in terms of this. Even text mode will be a little bit challenging. What is needed for this is to create a character generator, meaning we have some byte in memory like A, and then we need a character generator with, even this is challenging because we are running a little bit out of memory and logic elements. So the minimum requirement would be to have a character generator. Of course, there are already examples for this. The question is like FPGA examples for text mode, character generator. They are out there. The only challenge is to squeeze it somehow in the quite constrained logic elements that we are here. I hope you find this interesting and inspire you to do some stuff. You see, even we can do this here in a lunch break. Totally no worries here. So super easy. These examples just work. Even on our unsuccessful one-man, that is neither unsuccessful nor one-man, just a little bit recurring running gag of critical YouTube comments here and fans in the audience. So even in T2 this works. Everything packaged up nicely. I will send this makefile change to Clifford. You see here now we have here the stuff is just finishing up, probably in some 10 minutes as I estimated. Probably should get some final printout sometime soon. If you have questions in the audience, contribute. Still a beginner to so questions in the audience for C++ and what you recommend that study to be capable of this. I'm not sure if most of the open source stuff unfortunately is, in my opinion, unfortunately is C. So for that, not even sure if you need C++ because I guess the open source, the Mesa RedV open source driver might be pure C, so some ANSI standard C++ book might be useful there. Most of the C++ stuff, the standard template library and other modern stuff surrounding that are usually not very much used in the open source world, except maybe for like Qt, KDE, that sort of thing, or Clang, LLVM. We could also another day test if this works with Clang. You see now this is Icetime, so now it's doing some timing simulation. By the way, this stuff is so cool, this open source stuff, it's even doing some simulation, so you don't even, if you want to get into this is a super amazing example from Clifford Wolf, because so not only is it doing some command unfound, oops, did I not patch all of those RISC-V or RISC? Why is this saying icepick? Where is this coming from? Oh, wait a second. Command not found. This is, wait a second. Path. RISC-V GNU. Maybe it wasn't in the path. So now it's freshly reprogrammed this. So what we have done now is, while we were talking and giving you the summary, we fully resynthesized and reflashed this here, freshly synthesized, and even the firmware compilers we made make clean. So the other day I've also seen this doing a full emulation here of the FPGA, including the full serial output. One was running, of course, a little bit slow here on this aging Core i7, but you don't even need the hardware to get into this. Right now you can, this is a super amazing example, just clone this Git repository and you have even an FPGA simulation here with the open source toolchain. And so this is apparently maximum clock frequency of 15 megahertz with a design target here, probably in the make file of 13. I guess it's set somewhere in the make file. Yeah, frequency 13, there we have it. And when we connect there, is this what we, did we time some 2 megahertz? Anyway, maybe the pipeline still is divided, the clock is divided for that. Anyway, you see, I hope this works. And this toolchain is so much more amazing. Just Google for commercial FPGA toolchains on Windows. They sometimes have a Linux one that is more often segmentation faulting than not. So this open source toolchain, totally amazing. Also reattach here. And yeah, here's also the memory. And yeah, this will be quite challenging actually. And to integrate the HDMI output, so we need to connect, we need to like design a small FPGA character generating video graphic adapter thing, and where even my here or there or the other, and connect this to the bus here of the Pico RISC-V, maybe here, yeah. So this is the schematic here, SRAM, UART, that is what you see here, the SPI flash controller, Pico RV32 ISA, and the firmware is, so this is the SRAM, the UART that we connect to, the firmware living in the flash. And what we would need to do here is having like our, here on this circuit kind of stuff on the 32-bit system bus, design a tiny graphic adapter tiny as like, yeah, we only have 1000 something logic elements left and need to figure out where we connect the connect our character generator video memory to. But yeah, that is for the next project there, next weekend or something of that sort. Totally fun stuff. As I said previously, instead of playing Tetris or Sudoku, so much more entertaining here, in my opinion, much better hobby and spending of time to get into such kind of stuff. I hope this was a useful summary and testing all this stuff, and that it's working just beautifully as you see here. And where was the other, maybe that here of, here is our terminal. Hope you learned something and found this interesting and inspiring to do stuff yourself here with this kind of things. And what other comments do we have here? Fixing last sentence. Welcome. C++ is easier to learn but harder to correctly without templates and new stuff. Yeah, anyway, otherwise leave comments below the video. And yeah, also probably I made already the low-level code for DOS, and also coming up next is using this low-level examples with 3D acceleration for the Verge and Voodoo, and make one repository with this DOS examples, with this low-level drivers, and also with ARM, Spark, MIPS, and this PicoSoc. So right now it's running the firmware. That is an example firmware here, but most likely I will also port my DOS code and all this low-level stuff to have one low-level firmware stuff for DOS, MIPS, Spark, ARM, and this FPGA stuff. And then yeah, HDMI output, because that is, there you see this is all the programming stuff. Just connecting this right now will of course do nothing, because right now we have nothing driving the output here for the HDMI transmitter. That would be then real programming and integration of this FPGA design. So that's coming up next, and I hope to see you soon for all the next videos and tinkering to come.